All right, let's just dive right into this. Welcome back to another explainer where we take complex, invisible systems and break them down so they make perfect sense. Today, we're tackling a question that seems simple but is actually pure magic. How do computers actually talk to each other? We're going to break down something called the OSI model. And, as promised, I'm going to explain this to you like you're 5 years old. I know OSI model sounds super technical, right? But stick with me, because by the end of this, you'll see it's really just a beautifully organized game of teamwork.
So let's just stop and think for a second. How do computers talk to each other across the entire world? Literally, you type a message on your phone in New York, hit send, and boom, almost instantly, it's on your friend's screen in London. How on earth does an email cross the ocean from your piece of glass and metal to theirs? There isn't one giant wire running straight from your pocket to theirs, right? Instead, there's this invisible, highly structured process happening behind the scenes, making sure it works flawlessly every single time.
And that brings us perfectly to the OSI model. OSI stands for Open Systems Interconnection, and you can basically think of it as a universal language. See, back in the early days of computing, different brands just couldn't talk to each other. A computer from company A was literally incapable of sending a file to company B's computer. It was a mess. So in 1983, reps from major tech companies got together and wrote a master rulebook. It's a standard that lets any device, no matter who made it, talk over a network. It became our universal translator.
Now, the coolest part about this model is this specific number, 7. The folks who made the OSI model didn't just write one giant, confusing manual. Instead, they took the incredibly messy job of sending data and chopped it up into exactly 7 bite-sized jobs, or layers. Think of it exactly like a stack of building blocks. Every single time a message is sent, it has to move through these 7 blocks one at a time. So let's build this stack together.
First up, we're exploring the top layers. That is, layers 7, 6, 5, and 4.
We're starting at the very top, the software layers. These are the ones closest to us, the users. The absolute peak of our block stack is layer 7, the application layer. You can think of this as the actual apps we use and see every day. When you open up your web browser or your email app like Outlook, you are interacting right there at layer 7. It provides the services your software needs to talk to the network. Browsing the web, layer 7 is using HTTP. Sending an email, it uses SMTP. The big takeaway here is that this is the window where you, the human, hand your message over to the machine.
All right, so you've handed off your message. Now it drops down a block to layer 6, the presentation layer. Think of this layer as a mix between a secret agent's decoder ring and a super fast translator. Let's say your email needs to be compressed, so it sends a bit faster. Or even more importantly, it needs to be locked up and encrypted so nobody spying on the network can snoop on it. Layer 6 formats, translates, and encrypts your data. It basically makes sure that when your message finally gets to the other side, the receiving computer will actually know how to read it.
Next, we drop down to layer 5, the session layer. I really love to picture this one as a digital meeting room. Because before two computers can just start throwing data at each other, they have to formally introduce themselves, shake hands, and agree to keep the line open. Layer 5 sets up this whole meeting. It manages the connection while the data transfers, and then, very politely, it closes the door and ends the session when the message is fully sent. It keeps everything neat and tidy, so your private email doesn't accidentally get jumbled up with, say, a YouTube video somebody else is streaming.
Then we hit layer 4, the transport layer. This is where things get super active. Imagine layer 4 as a highly efficient post office. If you're sending a massive email with a giant photo attached, that's just way too big to shove through the internet all at once. So our post office chops your big message into much smaller, manageable boxes. We call these packets. It clearly numbers every single box so they can be rebuilt in the exact right order later, and it double checks to ensure absolutely 0 boxes go missing in transit. Okay, moving further down the stack, now we're exploring the bottom layers, layers 3, 2, and 1.
If the top layers were all about packing the message, these bottom layers are the invisible roads, delivery trucks, and the actual pavement carrying our boxes. So our tiny boxes first arrive at layer 3, the network layer. This is basically the GPS system of the entire internet. Our boxes need to know where they're going, right? So layer 3 slaps a destination IP address onto every single packet, kind of like writing a global zip code on a letter. Then, it acts as a super smart router, calculating the absolute fastest, least congested highway across the globe to get your data where it needs to go.
While layer 3 is up there figuring out the massive global map, layer 2, the data link layer, handles the local hop-to-hop delivery.
Think of Layer 2 as the local delivery trucks, driving your boxes from one specific intersection to the very next one. It uses things called MAC addresses. These are unique hardware addresses baked into specific devices. This ensures the data gets physically handed off to the correct router or switch on your local street. It also double-checks for any potholes or errors that might have happened on that little local stretch of road. And finally, we hit rock bottom. Layer 1, the physical layer. And this is exactly what it sounds like. We are completely done talking about software and data packets. Now we're talking about the actual physical stuff that moves the information. Your digital boxes are magically converted into raw electricity shooting through copper cables, or radio waves bouncing off your Wi-Fi router, or even actual pulses of light zooming through glowing glass fiber optic cables resting at the bottom of the ocean. This is the raw, physical transmission of ones and zeros.
So, let's put it all together. Here is a practical example of sending an email overseas.
To really lock this in, let's trace the exact journey of a single email traveling from a sender in New York to a receiver in London. We start in New York. You type your message, you hit send on your app. That's layer 7, the application layer, grabbing the data. Immediately, layer 6 encrypts it so it's locked tight. Then, layer 5 reaches out across the world to establish that meeting room session with the London server. Once they connect, layer 4, our post office, takes your email and chops it up into thousands of tiny, numbered packets. Your message is officially prepped, boxed, and moving down the stack.
Now their boxes hit the hardware. Layer 3 stamps that London IP address onto every packet, just like a global GPS coordinate. Layer 2 loads those packets onto local digital delivery trucks to move them out of your building and into your internet provider's network. And then Layer 1 takes over. Those packets are instantly converted into actual flashes of light, zipping down into massive fiber optic cables lying on the dark floor of the Atlantic Ocean, traveling thousands of miles in literally a fraction of a second. And when those flashes of light finally hit the shores of the UK and arrive at the London server, the whole process just runs in reverse. It rapidly climbs up the stack. Layer 1 catches the light signals. Layer 2 checks them for errors. Layer 3 confirms, yep, this is the right IP address. Layer 4 catches all those tiny boxes and glues them back together in perfect order. Layer 5 politely closes the meeting room door. Layer 6 decrypts the secret code. And finally, Layer 7 presents the fully reassembled message, popping it right into your friend's inbox. Boom. Utter magic. All right, before we wrap up, let's quickly talk about OSI versus TCP/IP. Now, I have a tiny secret to share with you. While the 7-layer OSI model is fantastic for learning, and it's literally the gold standard for teaching networking, there's a slightly different model that actually runs the modern internet we use today. It's called the TCP/IP model. It was created by the US Department of Defense, and it's actually older than OSI. The main difference? TCP/IP is just simpler. It takes those 7 layers we just learned and squishes several of them together. For example, it combines the top 3 OSI layers, application, presentation, and session, into just one big application layer. It's a much more streamlined model for actual engineering, whereas OSI is the detailed map we use to understand how everything connects universally.
So, if the actual internet uses TCP/IP, why on earth do we still care about the 7-layer OSI model? Well, it comes down to 3 massive advantages. First, it remains the ultimate universal language for all hardware and software vendors. Second, it makes troubleshooting incredibly easy. If a website won't load, an IT pro can test the physical layer, hey, is the cable plugged in? Then the network layer, is the IP address right? It isolates problems beautifully. And third, it's super flexible. You can invent a brand new Wi-Fi technology down at layer 1 without having to rewrite the web browsers up at layer 7. It is truly a marvel of modern engineering, all disguised as a stack of 7 simple blocks. Next time you click send on a photo, an email, or a text, I really want you to ask yourself, can you picture those 7 invisible layers? Just think about your data being encrypted, chopped into tiny boxes, stamped with a digital GPS coordinate, and fired as a beam of light across the ocean floor, only to be perfectly rebuilt on the other side. It is invisible, highly organized magic happening all around us every single second. So, the next time your Wi-Fi drops or a web page won't load, which of the 7 layers do you think is to blame?